Oh no.
According to Newton's first law, an object in motion tends to stay in motion. However, here on Earth, all objects in motion come to rest eventually. This is because of friction. Friction is always going in the opposite direction that an object is moving. As this ball moves to the right, friction is pushing on it to the left and causing it to slow down and go to a stop. And we're going to show you another example of friction. Although friction slows objects down, it's also required for motion. So with this car, as the little rectangles push on the ground in this direction, friction is pushing it forward and allowing the car to move forward. And friction also varies depending on which surface it is.
Ring, 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 ring. Tension force is when you transfer force through another object. Usually this is accomplished through things like ropes or strings, chains, things like that. Tension force can be used for pulling objects, but not for pushing. For example, we have this ball attached to a chain, and it's being held up by another object. Here the chain is pulling on this, so we can't really, it always holds it in its current place. However, and here you can see, so here we can pull on it, but when you push it, it doesn't really work. Of course, one of the main uses for tension force is to, say, have a car pull a trailer. So in this case, we have a car pulling a trailer.
Perfect.
Newton's third law states that for every action there is an equal and opposite reaction. The force that causes this to be true is called normal force. Normal force is the reactionary force to a contact force. You don't sink through the floor because the floor is projecting an equal amount of force on you. This also explains why you can punch through a wall. The equal force of your fist on the wall is being exerted by the wall on your fist. This physics book has enough normal force to support this rock so that if I were to place it on the book, place the rock on the book doesn't change shape in order to stop the rock from moving. Now, this beanbag, which Harry is now holding up, does not have enough normal force. So, when we drop the rock onto this, it collapses.
Play it? No, he isn't. Let's play it.
Also known as drag, air resistance is friction that's applied to objects moving through the air. While it doesn't usually apply to smaller moving objects, it comes into play when objects with a large surface area catch air particles. When this happens, the friction resists some of the applied force. A nice example of this is Galileo's classic experiment, where he dropped two different sized objects from a building and both hit the ground at the same time. And here we can see that, not accounting for any air resistance, just with these two circles. This one is considerably heavier than this one. As you can see, both fall at the same rate. However, if we turn on air resistance, you can see that over time, this one will fall a great deal faster than this one. That's because the air particles are catching and having a much greater effect on the lighter object than on the more massive one.
As the name suggests, applied force is the force of one person or object being exerted on another person or object. Applied force is only relevant when it is being applied as it is only a contact force. So to clarify, an applied force is being exerted on this rock while it is in motion from being launched. But as soon as it leaves Galen. As soon as it leaves the catapult, which is about right here, there's no longer an applied force being exerted on it because it's out of contact. Instead, that applied force has given the rock a velocity.
Need to do this.
How did you do that?
Spring force is the result of a stretched or compressed object attempting to return to equilibrium. In other words, when an object is deformed, as in bent, stretched, squeezed, and so on, it'll attempt to return to its original shape. A really good demonstration of this, is springs, obviously, spring force. What springs always do is they have a normal length, and then when you either compress them or stretch them, they always attempt to come right back. So here we have a little slingshot. So if we drag this down and release it, the springs attempt to return to equilibrium and launch everything that they're connected to.
Okay, so everything has a gravitational force when near an object with a large mass, like a planet. For a really massive object, gravity is pretty significant. In fact, it pulls down at 9.8 meters per second. Gravity only pulls, and it pulls towards the center of the massive object. Since we're on the outside of the Earth, gravity looks like it's pulling down because the core of the Earth is downwards relative to us. In space, gravity looks a little bit different. As distance from the object increases, gravity decreases. The objects closest to the Earth aren't close enough to be pulled into the Earth, but are instead suspended in orbit.
Oh. Physics is delicious.
Do it now!
We're talking about normal force.
That's right.
Yeah.
Talking about some normal force.
Are you gonna read the script or not?
No.
Well, the camera's rolling.
I noticed that.
Okay. Yeah.
When I drop this rock,
Rocky, no! His handle has broken. Curses.
the book doesn't change shape.
We're gonna have to refilm that. We're into hour 5 of recording.
That was easy.
It's not easy. We're tired. Have to pee. Haven't eaten in hours. This is horrible.
5 hours.